Right, well, good afternoon. This year's Electric Universe Conference is on the theme of the works of Emanuel Velikovsky, and I'd like to take this opportunity to do the same. And the subject I've chosen today, as you can see, is the anomalous planetary periods in the Pañchasiddhântikâ revisited. Velikovsky used this work in support of his theory in worlds in collision. And following Velikovsky's work, the electric universe model builds on that. Now, much of Velikovsky's documentation for worlds in collision is based on interpretation of myths, legends, and images. But the Pañchasiddhântikâ offers a rare chance to use data from ancient astronomical sources to support the theory. So these observations of all the planets seem to indicate that the Earth's year was only 360 days long in the past. But Velikovsky went further. Velikovsky also claimed that Mars and Venus of the synodical table must have had orbits different from their present ones, even if the terrestrial year was only 360 days. Velikovsky's interpretation of the Pañchasiddhântikâ is therefore of key importance for his whole thesis in worlds in collision and for the electric universe model. So the question is, was he right? Now in this talk I'd like to introduce the Pañchasiddhântikâ and analyze the anomalous data. That'll give us a chance to check Velikovsky's conclusions and also, finally, to discuss how the anomalous data might have arisen. So to start with the Pañchasiddhântikâ, the word in Sanskrit or Hebrew means the 5 systems of ancient Hindu astronomy. Well, it means the 5 systems. That is, they are doctrines or mathematical rules for computing the motion of the sun, moon, and planets. The 5 Siddhanta are copies of ancient astronomical manuals which were compiled by Vajramihir in about 550 AD. But the originals he was using are now lost. What we do have are 2 manuscript copies of Vajramihir's original text, which are owned by the Bombay government. And we know that the earlier copy dates from 1616, and the apparently later one was certainly in existence by the 1870s, but its original date is uncertain. The work of Vajramihir was translated from the Sanskrit by Thibaut and Dwivedi in 1889, and more recently by Neugebauer and Pingree in 1970-71, and again by Sastry in 1993. Because of the anomaly in the codicil, which we'll come to, one of the key questions is how accurately Vajramihir made copies of those original texts which we no longer have. But Thibaut was in no doubt. Having translated the entire Pañchasiddhântikâ, he was convinced that Vajramihir faithfully renders characteristic features of the Siddhantas as he found them. And also Vajramihir has in no case obliterated the characteristic features of the Siddhantas. So it seems that Vajramihir accurately reproduced in all essential details the ancient texts he had access to in around 550 AD. So what are the 5 Siddhântikâ? The 5 Siddhântikâ, which Vajramihir originally replicated, can be dated approximately by their style and content. And according to modern thinking, these are the Sara Siddhanta, dates from around about the 5th century AD, and was current at the time of Vajramihir's work, and a modern version of that still exists today. Further back, the Ramaka and the Paulissa Siddhantas are evidence of Roman astronomy in India, so therefore probably round about the 1st to 2nd century AD. Older still is the Vasita Siddhanta, which shows the transition between early Hindu and Greek astronomy in round about the 3rd to 2nd century BC. And the oldest of the Siddhantas is the Paitama Siddhanta, which shows the pre-Greek stage of Hindu astronomy. And there is also the anomalous codicil. Now, a little bit of background. Greek astronomical ideas began to enter India from the 4th century BC, following the conquests of Alexander the Great and the formation of the school at Alexandria. So the doctrines in the Pañchasiddhântikâ must therefore date back to before the 4th century BC. And what's striking is how long these traditions were preserved. Remember that Vahar-Mihir was only writing the Pañchasiddhântikâ in the 6th century current era. So I suggest this gives us an insight into Vahar-Mihir's motives. In modern terms, he was presenting a review of earlier theories which showed the development of Hindu astronomy over the centuries. And I think that's why he included the anomalous codicil. It was part of the ancient texts he had access to, and so he probably felt he had to include it in the Pañchasiddhântikâ, despite being aware of its anomalous nature. So what is the date of the anomalous codicil? The 5 Siddhântika all agree nearly exactly with the modern year length and planetary motions. And these have been known since Neo-Babylonian times, that is from the 8th century BC. Going further back, the modern practice of dividing a circle into 360 degrees began with the Sumerians. But during the 8th and 7th centuries BC, the Babylonians developed a new empirical approach to astronomy. And there was a significant increase in the quality and frequency of Babylonian observations, which appeared during the reign of Nabonassar, 747 to 734 BC. I'm using conventional dates, of course. The last stages in the development of Babylonian astronomy took place during the time of the Seleucid Empire, 323 to 60 BC, and so the Babylonians were in part contemporary with the Greeks, whose ideas they copied, or rather the Greeks built on the Babylonians' ideas. Now Hipparchus, in the 2nd century BC, compiled a list of Babylonian astronomical observations. And Hipparchus's tables go back to 747 BC, that is some 600 years before his own time. Apparently Hipparchus didn't go back any further because he considered that the earlier Babylonian records were inconsistent with the motions of the planets of his time. Now, in contrast to the 5 Siddhanta, the codicil's planetary data is anomalous. It doesn't agree with modern values. So if it's a genuine survival of some very early observations, then it must have originated before the start of the Babylonian data in 747 BC and been preserved over the centuries like the Pañchasiddhântikâ was. I think the fact that early astronomy was closely tied to ritual and religious observances make it very likely that these ancient doctrines would have been preserved accurately over the centuries. So let's have a look at the anomalous codicil. It only amounts to the last 2 pages of 103 pages in the total Pañchasiddhântikâ. It appears as verses 64 to 81, which are appended to the Paulissa Siddhanta, but they're not part of it. They appear after the concluding colophonic verse, which formally ends the Paulissa Siddhanta, and they're written in a different poetic meter, and they have a different style entirely. And they're also introduced by Vahar-Mihir in tongue-in-cheek fashion. So Vahar-Mihir clearly recognized that the data in these verses was anomalous, but he obviously wanted to include them as they stood without commenting further on the discrepancies. So here's an example of the codicil text for Mars. In verse 67, the important numbers are 4 and 3075. These indicate that the observations covered 4 synodic periods of Mars, which took 3075 days in total, and so Mars's synodic period is 1 divided by the other, or 768 3/4 days. Verses 68 and 69 then give the time taken for the various stages of Mars's synodic period, as seen from Earth. The days add up to 768, the degrees add up to 360. These 2 verses therefore confirm the synodical period given in the first verse. And each of the 5 planets has a similar set of 2 measurements. And we're going to concentrate on the first set in each case, which gives the synodic periods directly and slightly more accurately because of the numbers of periods counted in each case. So here's a summary of the codicil data, taken from Thibault's translation. We've already seen that the 4 periods of Mars were counted, amounting to 3,075 days of observations. The shortest period of observation was for 3 synodical periods of Saturn, and that is for over 9 years of observation. And the number of periods counted ranges from 2 to Venus to 29 for Mercury. So how does that compare to the modern day figures? Well, here's the comparison to present day figures, and the last line shows the differences as quoted by Velikovsky. Note that Velikovsky didn't give the exact differences, and I don't know why, but he must have noticed that the Venus and Mars have bigger numerical differences than the other planets, and perhaps that's why he singles them out. So the differences are obvious. What's the reaction to the figures? Thibault, the original translator, was puzzled by the figures, which he called startling. But, as we've seen, he'd been impressed with the accuracy of Vahar-Mihir's original copies, and so Thibault concluded that we can hardly help accepting the rules as they stand. Of course, astronomers such as Neugebauer and Pingree know that the solar system clockwork has run unchanged for many millennia, and so they explain the discrepancy as a mistake by Vahar-Mihir, who must have confused days and degrees. But as Michael Reed pointed out in the SAS Review 1980, this amounts to an admission that the figures agree with the 360-day Earth year. Other astronomers, such as Sastry, simply dismissed the whole codicil as a spurious insert by some later ignoramus. But I think Thibault was probably right, and the figures may be a genuine record of ancient observations. So let's see where that leads to. This society has looked into the question before. Dr. Fourmer gave a presentation to the SAS meeting in 1979 and published an article in the following review. And Michael Reed, who I've just mentioned, produced an article in a later version of the review, 1980-81. Now, my analysis is going to be broadly in line with Reed's conclusions, but with a very different emphasis. Let's remind ourselves what a synodic period is. It's the time between successive conjunctions or oppositions of a planet. That is from one alignment with the Sun to the next, as seen from Earth. The Earth can either be the inner planet or the outer planet in this diagram. It just depends which other planet you're looking at. Because the planets orbit the Sun at different speeds, alignment of the Sun, Earth, and any one planet involves a different number of orbits for the Earth and the planet before they come back into alignment at some different angle to the fixed background of the stars. So, if we anticipate the result we're going to prove, there are 2 possible explanations for a change in the length of the year. Either Earth's spin rate could have altered, which means the length of the day was different. Or Earth's orbit could have altered, while the day length remained the same. So, a simple bit of mathematics. This equation gives the synodic period SP for a planet in terms of its orbital period, TP, and the Earth's orbital period, TE, which is the length of the year. But if the length of the day was different, then the formula must include d dashed, which is the ratio of older days to present days. In this formula, s dashed and t dashed are the number of older days in the synodic and orbital periods, respectively. Now lastly, if the Earth's spin rate was different, we can get a direct solution for the ratio of the old day to the present day using the first formula. But if Earth's orbit was different, then there are 2 unknowns for each planet. That's TP dashed and TE dashed, assuming that we don't yet know the answer includes an Earth year of only 360 days. So what's the solution for a change in the Earth's spin rate? If we do the maths, we find that the ratio of an older day to a present day is the same for every planet. So we can easily work out that the old Earth year was only 360 days, as Velikovsky and Thiebaud knew from the codicil data. But note that this solution is the same for all the planets, including Venus and Mars. So it's not clear why Velikovsky singled those two planets out as being on different orbits, if the Earth's spin rate was different. Just a slight aside, how might we accelerate the spin rate? Reid suggested that this solution was the likeliest, but is it realistic? How could the Earth's spin rate be accelerated so as to fit more days into the year? Now, there is some evidence that small changes do occur in the present era. For example, small temporary changes in the length of day are observed during solar storms and coronal mass ejections. But a permanent change in the length of day requires a large external torque applied for a long time. Now, maybe one possibility we could consider is Alfvén's mechanism. In 1941, Alfvén rediscovered the co-rotation mechanism previously postulated by Ferraro and Chapman. What happens is that any plasma in the equatorial plane of a rotating planet with a magnetic field is accelerated up to the same angular rotation rate as the planet. Now, it's obvious that this mechanism could also work in reverse, although very slowly. If there was a rotating plasma disk, then the planet's rotation could speed up to match it. But it's very difficult to see how a rotating plasma disk could have evolved and been maintained long enough to accelerate the massive body of the Earth. So although changing the Earth's spin rate was Reid's preferred solution, I'd rather look at the alternative of changing the Earth's orbit. Now, remember that if Earth's orbit was different, then we have an equation with two unknowns, and we have to use the data from at least two planets to get an answer. So we'll start off with Saturn. We know that the solution must lie somewhere on the blue line, relating the old Earth year and the ratio of the old orbital period to its present one, where the y-axis has been scaled so that we can compare the different planets. If we now add in the line for Jupiter, we see that we've got a single solution for both planets in terms of the ratio of their old and new orbital periods. Note that the old Earth year is again about 360 days, but this time the days are the same length as our present days, and the change is due to the changed Earth orbit. The other thing to notice is that the periods of Saturn and Jupiter are also altered. They're only about 98.5% of their present ones. So what happens if we add in Mercury? Mercury follows the same pattern. It confirms the 360-day Earth year, and its period was also only 98.5% of its present one. So the key question, what happens to Venus and Mars? They follow the same pattern too. All the periods are only 98.5% of their present ones. All right, so that's the periods. What is the effect on their orbits, which Velikovsky referred to? Using Kepler's third law, we see that the effect is that the orbital radii of all the planets, including Earth and Venus and Mars, were only 99% of their present ones. In other words, the solar system would have been about 1% smaller than at present. So, to summarize the result, if Earth's orbit was different, the year was 360 days long, and if Kepler's law holds, then all planetary orbits were about 1% smaller. And that means Velikovsky was incorrect to single out only Venus and Mars as having different orbits. These planets behaved in exactly the same way as the others, including Earth. There's nothing to suggest that they'd altered each other's orbits by near collisions. That's an important conclusion for the electric universe's model. But I'd like to spend the last few minutes of this talk explaining very briefly how all the orbits might have increased by about 1%. The Titius or Titius-Bode law gives the relative lengths of the planetary orbital radii as a geometrical progression in the form 2 to the power of n, where n is the number of the planet from the Sun, counting Mercury as 0. Now, the reason I'm not entirely comfortable with using Bode's law, Bode's name with the law, is that Titius published his law in 1766 as a footnote to a translation of another paper. The German astronomer Bode read this and reproduced Titius' law in a paper of his own in 1772, but without initially crediting Titius for its discovery. Now, of course, Titius himself may have got the idea for his law from earlier works by either von Wolf in 1723 or possibly James Gregory in 1702, but we're rather drifting off the subject. The point is, Titius' law works fairly well, especially for the planets closest to the Sun. And that reminds me of Alpha's plasma co-rotation, which we saw earlier. Because further out, that law breaks down as well. Now, there are 3 other examples of a Titius-type law in the solar system. The moons of Jupiter, Saturn, and Uranus all have a similar geometrical progression. According to Dermot, 1968, these can be expressed in terms of the planetary periods as Tn is T0 times a to the power of n, where a is the square root of 4, 2, and 3 for Jupiter, Saturn, and Uranus, respectively. Now that's quite nice, because as Dermot pointed out, the Pythagoreans would have liked this rule. Expressed in terms of orbital radii, it reads that the radius cubed is the original radius cubed times a squared to the power of n. Or, the volumes of the mini-celestial spheres defined by each planet's moons are in a simple numerical ratio, and so they appear in harmony. Now, whether it's harmony or something else, it does seem as though some process in the solar system determines the spacing of the planets and the moons of the major planets in a very similar way. So, what does Titius' law actually mean? Well, it appears to represent a set of stable solutions to the orbital equations. So whatever changes the solution for one planet or moon changes the solutions for all the planets or moons in equal proportion. We don't yet know for certain why Titius' law seems to work, although some researchers have suggested that it may be related to orbital resonance. But whatever it eventually turns out to be, if we assume that there is a real physical reason for it, then we can understand in principle the 1% change in the orbits of all the planets suggested by the anomalous data in the Pañchasiddhântikâ. And one thing we shouldn't overlook is that Kepler's law relating a planet's orbital period to the orbital radius assumes that the product of the gravitational constant g and the Sun's mass m is constant. Well, of course we think it is today. But can we be absolutely sure that it's always had the same value in the past? Was the Sun's mass always exactly the same? Or might g have changed? Now that's a subject for another day, but I'd just like to mention a few tantalizing thoughts. We know that g is the most unconstant constant. It's notoriously difficult to measure g. Experiments keep giving different values. And during solar eclipses, there's the anomalous behavior of pendulum swing rates known as the Alfvén effect, which seems to indicate a quite dramatic change in g. And there's also observations of changes in atomic clock rates during eclipses, which suggest that things aren't as constant as we like to think they are. And finally, modified Newtonian dynamics is a theory proposed to explain the flat rotation curves of galaxies, and it postulates a variable g. So perhaps g and or the mass of the Sun weren't exactly the same in the past, and may have contributed to the 1% difference in the set of stable planetary orbits and periods. So to summarize, The anomalous codicil to the Pañchasiddhântikâ is, I think, probably a genuine record of ancient observations. It indicates an Earth year of 360 days in the past to a high degree of accuracy. It's unlikely that the change to the present year length could have been due to a change in the Earth's spin rate. If the Earth's orbit was different, the Earth's year again would have been 360 days, but it seems that Titius' law would still apply. All the orbits were just 1% smaller. And the orbital change could perhaps have involved a change in g times the mass of the Sun in Kepler's third law. But my main conclusion for today is that Velikovsky was wrong. The figures in the Pañchasiddhântikâ show very clearly that there were no worlds in collision. Thank you for listening.